Hello everyone, this is the third video on the open mock paper. We'll be going through questions 11 through 15. And this is the point where things start to get really tricky for a variety of different reasons. Tricky could be because the solution is lengthy, tricky could be because it appears very tedious, or tricky could just be quite difficult to think of. We're going to see an example of probably each of these somewhere in these 5 problems. For question 11. ABC is a scalene triangle with BC equals to 100. DEF are on side BC such that AD, AE, and AF are an altitude, angle bisector, and median respectively. We are also told that DE is equal to EF. And we are asked to find the floor of AB plus AC. Now, there could well be some clever geometric way of doing this, but to be honest, that wasn't really my intention here. Instead, how I wanted to solve this is largely going to be computational. To begin with, I don't really like the 100 when doing most of my computation, so I'm going to scale it down first. I'm going to just scale it down such that f being the midpoint just divides these two into 1 and 1. Right, so I'll scale down by 50 times. We have to write this down so that at the end of the question, we remember to multiply back by 50 again. Now, I will call these in the usual side lengths, B and C. And then we have got DE equals to DF with these angle conditions. So angle bisector as well as a rectangle. I'm going to just simply write down what BD and BE are, or rather, I can't just write it down, but I'm going to just find what it is. And both of those are not very difficult tasks, because for BE, I can use the angle bisector theorem. And the angle bisector theorem just tells me that BE over EC is C over B. So it divides this length 2, BC, in the ratio C is to B. So BE is going to be equal to C over B plus C times 2, which is what we can do for now. We have also got AD, and AD I can find it using the cosine rule to get this angle first, and then after that extract out AD. Sorry, extract out BD, I should say. So by the cosine rule, cosine B should be equal to C squared plus 2 squared. Mouse is not allowing me to write the number 2. 2 squared minus B squared over 2 times C times 2, which is 4C. And BD is actually C times cosine B. So just nice, you multiply C to this. Okay. Now, we must remember that the final equation we are dealing with is DE equals to EF. Now, another way of saying DE equals to EF is that BD, BE, and BF are in an arithmetic progression, meaning that BE is the average of BD and BF. And perhaps that's the easiest way that we can form an equation so that we don't have any unnecessarily messy terms to work with. Right, so BE should be the average of BD and BF, means 2BE is equal to BD plus BF. Okay, so let's write that all down. 2 times of BE. So 4 C over B plus C is equal to BD. Alright, plus 1 for 2 squared over 4. And then plus BF is 1 again. So actually that would be just plus 2. And this kind of looks like it should be able to simplify in some way. It is not so clear how exactly you simplify, but let's just multiply everything by 4B plus C and we'll see. Now, we don't want to create a huge mess. So again, alluding to the theme of symmetry, how do I keep this nice? The easiest way to keep it nice is to subtract this over from the other side. So that in doing so, we are going to have 8C minus B equals to C squared minus B squared. Oops. B plus C. Okay, so C minus B is actually a factor that we can take out from both sides. It is scaling, so we won't have B equals to C. And in any case, if it were isosceles, then D, E, and F all be the same point, which is not what I wanted to happen. So 8 equals to B plus C squared, and B plus C is 2 root 2. Now remember, that's not the answer because we scaled down by 50 to avoid the big number. So we shall scale it back up by 50 again. So floor of K is floor of 50 times of this is 100 root 2. Now this problem is here because the SMO has had the tradition of requiring you to know the square root of 2 or the square root of 3 to something like 2 decimal places. So I thought it was important to also have a question that turned out to require that. And square root 2 is 1.414 to 3 decimal places. We only need 2 of them to say that it is 141. Question 12 is actually a lot easier than it looks. We need to start off by looking very carefully at 30720 and trying to figure out what is that. And whenever you have this sort of find the remainder questions, it is probably something to do with modulo arithmetic. And when it's modulo arithmetic, it would be useful to prime factorize this 30720. Now, it is a multiple of 10 and a multiple of 3, so I'll just take out 30, and 1024 is a power of 2, is 2 to the power of 10. So the factorization is actually 2 to the 11 times 3 times 5. Okay, so it suffices for us to split it open, but then again, it is obviously divisible by 3 and 5. How about 2? What is it divisible by 2 to the power of 11? Well, if we go from 1 up to 2022 and take the lowest common multiple, the number with the highest power of 2 is precisely 1024. And 1024 is going to be inside. But not 2 to the power of 11. 2 to the power of 11 is 2048, which is beyond this range. So it is a multiple of 2 to the power of 10, which means that it is yes and no, right? It is divisible by 2 to the 10, but not 2 to the 11. So 2 to the 10 divides this, not 2 to the 11. And of course, 3 and 5 do divide it as well. So that means that if you want L2022 and to be divided by this 30720 and output the remainder, if I write it as 30720Q plus R, where R is the remainder, you know that R must be divisible by 2 to the 10, 3, and 5. But it does not mean that we can have R equals to 0, because if R equals to 0, we are saying that it is divisible by 2 to the 11. So the only way that it can happen is that R is equal to this. It cannot be 2 times this, because 2 times this would be just congruent to 0. So R is just half of this thing you're dividing by, which is 15360. Yeah, we know nothing about lowest common multiples without digging very closely into it. But for this question, you don't need to dig too much because it is a multiple of almost everything. It's common multiple. The only thing that we are missing is one factor of 2, so we cannot say that it is a remainder of 0. But it should be the next best thing, which is half of that. Okay. Next up is question 13. ABC is an isosceles triangle with AC equals to BC. D is on BC such that AD is an angle bisector. So let's mark out the equal angles first. In fact, I'll just put theta, theta, and 2 theta. Given that AD plus DC is equal to AB, find angle CAB in degrees. Now, there's actually more than one way you can do this problem. Because when you have these sorts of conditions, it is pretty ripe for a lot of things. Now, for example, one thing that you might consider doing is just to extend this out here, such that this is equal. Let me make it a bit shorter, because what should happen if you extend it out such that it's equal is that now this, let's say AE, should be equal to AB. So that's one way that this could go. Okay? And if you proceed, you will be able to do it. Another way, if you don't want to do it like this, is to use some trigonometry. Just let this length AC and BC be 1, and you would also be able to make some progress. Now, the way that I want to show is just cute. So I want to point out what can be done here, because this is a very useful idea for angle bisectors as well. The idea is that I'm going to draw a circle around ACD. Excuse the woeful drawing of a circle. And I'm going to call that intersection point E. Now, why did I do that? Well, the first reason why I did that is immediately this angle here is the exterior angle of the isosceles, of the cyclic quadrilateral, I should say. So it is going to be equal to 2 theta, and that gives you another smaller isosceles triangle. So we get an equal length here. What does this mean? Now, it means that, remember, AD plus DC is equal to AB. So we want to make use of that as best as possible. And how I want to use that is that by drawing a circle around this angle bisector. Now, I didn't want to just bring the 2 theta over. I also wanted the angle bisector. Because when you have an angle bisector, it means that CD would also be equal. CD and DE both subtend the same angle, so they must have the same length. Right? One way to say this is that angle CED equals to angle DCE equals to theta. And so therefore, CD equals to DE equals to BE. So I can change this to BE. And if I subtract that off on both sides, it means AD equals to AE. Which is a bit of a surprise. But a good surprise nonetheless. So another pair of equal lengths shows up. AD and AE. So we can now just angle chase a little bit. Since those two are supposed to be equal, and we know that this angle is supposed to be 4 theta, the exterior angle of this triangle. So 9 theta equals to 180 degrees, theta is equal to 20 degrees, and angle CAB is 40 degrees. Now, every time when we have a geometry question, the general response to the solution would be, why would you draw that circle down there? And the answer is twofold. One, maybe you don't need to draw that circle down there. Any other method that you use to get the correct answer is perfectly acceptable. But the other thing would be, at least do something that seems meaningful. And if it doesn't work, then do something else. And if it doesn't work, do something else. Basically, experiment with a geometry diagram the same way as you would experiment with an algebraic problem by, should I square it, should I add them, should I move it over? You don't regret it if it doesn't work. You just erase off that line and try something else. So do the same with a geometry question. Extend it, didn't work, erase. Draw a circle, didn't work, erase. Draw a perpendicular, didn't work, erase. Until you get something useful. And more often than not, there are a few different ways which are all viable for the same problem. Question 14. In the earlier video, I mentioned that question 9 was the first of the tedious questions, which I don't really like that much, but do appear in the SMO. This is the second one that I have put into this paper. Let fx be, well, a bunch of flaws. I don't want to read that out. Let y be the value in the range of fx such that absolute value of y minus 2022 is minimized, find y. In other words, the question is asking, how close can this function get to 2022? Right, what's the closest value it can be? Can it be 22 exactly? And if not, then how close can you go? The first thing that we would do is to bound f of x. Now f of x, we know that it is smaller than if you took away all the flaws and is x to the 5. But the floor of x is still going to be, well, yeah, not that far away. So if we have f of x is less than x to the 5, then let's estimate where it should be at least. Now f of 4 would be equal to 4 to the 5. For integer values, they are exactly the same. 4 to the power of 5 is 1024. So that's fairly far away. Now f of 5 is 5 to the 5. This is 3125, which is kind of equally far away if we are being honest. So at this point, you might ask, well, what do we do? And the answer, unfortunately, is that we will do a little bit of so-called binary search. Our answer is going to be between 4 and 5, for sure. We can say, therefore, that this inner one is going to definitely become 4x regardless. But other than that, we really say that much. We know that we want something to be around the middle. And because it's supposed to be in between this and this. So we can try 4.5. If you try x equals to 4.5, I'm just going to write it as a sequence of numbers. First you have 4, and then times 4.5, you get 18. 18 times 4.5, you get 81. 81 times 4.5, yeah, so this is where it gets annoying. You get 364.5, which rounds down to 364. And then after that, 364 times 4.5 is still pretty far away. It is 1638. So what do we do next? I said, sort of like binary search. So try the middle again, 4.75. Right now, that would be the thing that pushes this up to 19. So 4, then 19. 19 times 4 and 3/4 would give you 90.25. So that becomes 90. 90 multiplied by 4.75 gives you 427.5. 427 times this would give you 2028.25. So you get something that is remarkably close. And if you go any lower than 4.75, the point is that this innermost layer is going to drop by 1. So it's already going to be at most 18 in the second spot. In other words, if you go from 4.5 to 4.75, second stop will be 18. And you start from 18 and just keep multiplying 4.75 as an upper bound. You're not even going to get here anymore because, as you can see, this is a slightly smaller starting point by about 5%. So that's already too small. And I'll just give you the upper bound values. So at most 85, and then at most 403. And then this is going to be, well, something less than 2000. Now, specifically less than 1914, but you get the idea, it's pretty far away. Now, despite me saying you get the idea, I said this is not a very nice problem. This is just meant to mimic the style of the SMO Open, where there will be 1 or 2 problems of this sort. So if you are really stuck, don't rule out the most silly guessing approach like this. It once in a while pays dividends. And in this case here, it does give you the result, which the answer is 2028. Because any lower than 2028 is going to drop off by quite a lot. Any higher is going to be, of course, further away from 2022. So this must be the answer. Okay. One last question in this video is question 15. This is not a silly question like the previous one. This is meant to be a demonstration of how one would use the Cauchy-Schwarz inequality. If you have not heard of the Cauchy-Schwarz inequality, here's what the Cauchy-Schwarz inequality states for any number of variables, but I'm just going to use sets of 3. So if we have for sets of 3 variables, this is what Cauchy-Schwarz states. So on the left, you have the sum of squares times the sum of squares. On the right, you do geometric mean. So a squared and x squared becomes ax. B squared and y squared becomes by. C squared and z squared becomes ez. And you square this as well. So this is what Cauchy-Schwarz states in general. Now, in fact, for those of you who have learned vectors before, Cauchy-Schwarz is just equivalent to saying that uv is greater than or equal to u dot v. If you realize that this is just the same as that if you break up u and v into components for 3 dimensions. And it's true for more than 3 as well. It is just that for the example, to save some writing time, I use 3. Now, equality holds. When you say equality, means that the Cauchy-Schwarz inequality is telling you the left side is always greater than or equal to the right hand side. They are equal when a, b, c, and x, y, z are in the same ratio. And in vector terms, those are just parallel vectors. So equals to some constant, then you get equality. The question, of course, for those of you who already know Cauchy-Schwarz is like, yes, we get it. I know what's Cauchy-Schwarz. How are you supposed to use it here? Well, how you use it here is as follows. We can't change what is given to us on the given expression. But what we want to do is to say that this times something is at least equal to something nice. Now, remember that for 1 over x plus 1, you need to find something to pair up with it such that their product is a perfect square, or at least something like a perfect square so that the result is nice. So you would like to cancel off x plus 1. So what better way to do it than to put x plus 1? And likewise, what better way to do it than y plus 2 and z plus 3? Now, if you did this, then Cauchy-Schwarz would tell you this is just going to be more than 1 plus 1 plus 1 squared, which is certainly nice. But you might say, wait, that's useless. How is that useful when I'm getting x plus y plus z plus 6 down here? That's nothing to do with what I want. So indeed, that's true, and we need to just change it by making sure that we get 9x and 4y. Those are conveniently chosen to be perfect squares, so that you can change 1 and 1 here just to 3, 2, and 1. So this is 1/4, the given. This is 6 squared, this is 36. So we will get this to be at least 36 times 4, which is 144. We have got all these constants, so plus 9, plus 8, plus 3 is plus 20. So therefore, the minimum value, m, is 124. Now, for this problem, I wanted to make sure that everyone fully understood Cauchy-Schwarz. So I also asked, when does equality hold? And equality hold, as we have seen, when they are in the same ratio. So if these are in the same ratio, we can write down what that entails. So this over this is telling you 9x plus 1 squared is equal to 4y plus 2 squared equals to z plus 3 squared. That's the equality case. And I should probably indicate that I mean the equality case. So I'll use the x1, y1, z1 in the question. It means that simply the x1 plus 1, y1 plus 2, and z1 plus 3 are in the ratio 1/3 is to 1/2 is to 1. So their reciprocals would be in the ratio 3 is to 2 is to 1. And so they split up the 1/4 in the ratio 3 is to 2 is to 1, meaning that this should be 1/4, sorry, 1/6 of 1/4, so 1/24. This would be 1/3 of 1/4 is 1/12. And this is half of 1/4, which is 1/8. So x1 is equal to 7. y1 equals to 10. And z1 equals to 21. Okay, so this is how you would extract out the equality case. Just write down the equation and then go back to the fixed value part of it, which is that you know these sum to 1/4. So establish what ratio they're supposed to be in. And from that ratio, you figure out what exactly they are. So do the computation. 124 plus 7 times 10 times 21. And you get 1,594. And that's an example of Cauchy-Schwarz for you. With that, let's end the video here. It's been going on a bit longer than usual. We have 10 more questions, which are mostly difficult but pretty fun. So please look out for that. Leave any comments you have below, and hope to see you in the next video.